In our previous video, we were reviewing concepts of motion along a line, particles moving back and forth along horizontal and vertical lines. And today, we're going to let those particles venture out into the XY plane and work in 2 dimensions and even form paths that are curved. And we're going to use vectors to represent this kind of motion. Just a quick review of vectors. Hopefully, we have seen them previously in pre-calculus, possibly in physics. Vectors have magnitude and direction, and we represent them with a horizontal component and a vertical component. So this would be, for us, these are going to be parametric equations. Our horizontal component will be represented by x of t, and the vertical component represented by y of t. So if I have a vector x of t, y of t, this is going to be the position vector. And of course, our components here could be functions. The example I'm showing here, they're both constants, but they could be functions, which would result in a curved path for our particle. Now, when we work with motion and vectors, the concepts are really very similar to what we do with linear motion. It's just that we're going to be doing everything twice. So, for example, if I want to find the velocity vector, this will still be the derivative of the position vector. It's going to be x prime of t, y prime of t. So we're just going to take the derivative of each component separately. And likewise, if I want the acceleration vector, that would be the second derivative of x, x prime prime of t, and y prime prime of t. So hopefully that idea makes sense. Another thing we need to talk about here with vectors is speed. And if you remember from our previous video, speed is equal to the absolute value of velocity. When we're talking about linear motion, speed is velocity without direction. It's always a positive value. Well, when we switch to vectors in motion along a curve, speed is not just the absolute value of velocity, but it's really the magnitude of the velocity vector. The magnitude of the velocity vector. And so if I have the velocity vector here, where my horizontal component is x prime of t, my vertical component, here we go. Horizontal component is x prime of t, vertical component is y prime of t. The magnitude of this vector, I'm going to find that just by doing Pythagorean theorem. The magnitude means the length of this vector. And so x prime of t squared plus y prime of t squared, and then we're going to square root that. That's equal to, that's going to give us speed. Now, I could also write this, instead of using this prime notation, just to connect back to what we've already done with parametric equations. This may look familiar to you. Dx dt squared plus dy dt squared. This is also speed, but I do that to connect back to our formula for arc length with parametric equations. When we're talking about motion along a curve using vectors, then distance traveled, if I want to find how far our particle has traveled on a curve, what I want to do is sum up all of the speeds. It's still going to be an integral of velocity, but we're going to take the integral of speed from A to B, square root of dx dt squared plus dy dt squared dt. We're just summing up all of the speeds to get the distance traveled. It's the exact same formula for arc length, just when we're dealing with motion along a curve, then we're going to call it distance traveled. Okay, so with those ideas in mind, let's just look at some examples and see how we can apply these concepts to motion along a curve. Particle moves in the xy plane so that anytime t, the position of the particle is given by x of t equals t cubed plus 4t squared, y of t equals t to the fourth minus t cubed. Find the velocity vector when t equals 1. So we are given the components of the position vector. My velocity vector, which I can denote vectors using this little half arrow on the top, is going to be equal to, I'm going to take the derivative of the x component, 3t squared plus 8t. I'm going to take the derivative of the y component, 4t cubed minus 3t squared. And that is my velocity vector. Now we want this vector when t equals 1. So we're going to plug in when t equals 1. We're going to get 3 plus 8, which would be 11. I'll go ahead and show plugging it in just so we're clear about what we're doing here. But this is going to be equal to 11, comma 1. And that would be our velocity vector at the instant that t equals 1. All right, next we're asked to find the acceleration vector when t is equal to 2. So my acceleration vector is just going to be the derivative of the velocity vector, derivative of the horizontal component, 6t plus 8, derivative of the vertical component, 12t squared minus 6t, and that is my velocity vector. If I'm going to find the vector when t equals 2, that would be equal to 6 times 2 plus 8 and 12 times 2 squared minus, I was going to write t again, minus 6 times 2, turn that into a 2. There we go. And let's see, 12 plus 8, that would be 20. And 48 minus 12, 36. Sorry about that, kept it down too low. So that would be our acceleration vector at t equals 2. Okay, in this example, we have a particle moving in the xy plane so that any time t, where t is greater than or equal to 0, the position of the particle is given by these parametric equations. Find the magnitude of the velocity vector when t is equal to 1. Now, just as a reminder, magnitude of the velocity vector, that just means speed. That's really what we're looking for here is the speed. And so my velocity vector is equal to, let's find that velocity vector first, because what we're given here are the components of the position vector. So the velocity vector would be 2t plus 3, and the y component, 3t squared minus 6t. So that is our velocity vector. We want the magnitude at the time when t is equal to 1. So let's find, well, I slipped into old linear motion. Should have been velocity vector there. Sorry about that. So our vector when t is equal to 1 would be, that's equal to 5 and negative 3. That's the velocity vector at t equals 1. And so now we just want to find the magnitude of this vector, which is the formula that we have for speed, which is really just using Pythagorean theorem with the horizontal and vertical components of this vector. So speed is going to be equal to the square root of, just as a reminder, I'll write the formula. X prime of 1 squared plus y prime of 1 squared. We've got x prime and y prime. We're plugging in 1, which is the work that I did to get to these numbers. And so here, this is going to equal the square root of 5 squared plus negative 3 squared, which is the square root of 34. So that would be the magnitude of our velocity vector, or the speed at t is equal to 1. All right, example 3, we've got a different scenario here, a particle moving in the xy plane. So that the x component is equal to the square root of 3 minus 4 cosine t. Y is equal to 1 minus 2 sine t. T is between 0 and 2 pi. The path of the particle intersects the x-axis twice. Write an expression that represents the distance traveled by the particle between the two intercepts. Do not evaluate. Okay, so this problem is a little bit more complex than the examples that we've looked at so far. First of all, let's start with, well, let's think about where we're headed. Distance traveled. So our distance traveled formula, again, is the integral from a to b, square root of x prime of t squared plus y prime of t squared dt. Since this is a dt here on the end of the integral, that means that a and b are going to be time numbers. They need to be t numbers. And so those are the things here that I need to find. I can find x prime and y prime pretty easily because I have x and y, but I need to know my a and my b. And that's where this information comes in. The path of the particle intersects the x-axis twice. And we want to know the distance traveled between those two x-intercepts. So let's think about what that means. An x-intercept, if I'm on the x-axis, what that means is that the y-coordinate is equal to 0. And so we're going to take the y component here, and I'm going to set it equal to 0. And then I'll solve for t. So we have sine t equal to 1/2. And I know t is between 0 and 2 pi, so I just need to think, when does sine equal 1/2? That, of course, is at pi over 6 and also 5 pi over 6. So those are going to be the two t values for our integral. So now we can write this integral from pi over 6 to 5 pi over 6 square root of, I need the derivative of x. So here's my x component up here. The derivative of square root of 3, of course, is 0, minus 4 cosine t. The derivative of cosine is, well, the derivative of negative cosine would be positive sine. So this is going to be 4 sine t squared. Plus, then I need the derivative of my y component. The derivative of 1 is 0. The derivative of negative sine would be negative cosine. So this is negative 2 cosine t squared dt. And it did say write, but do not evaluate. And so we're done with that example. Okay, in example 4, a particle is moving in the xy plane so that any time t, the position is given by this set of parametric equations. T is greater than or equal to 0. For what values of t is the particle at rest? Now, this example brings up a pretty important difference when we're talking about a particle being at rest in the xy plane in two-dimensional motion. If we're just moving back and forth along a line, of course, particle at rest means that the velocity is 0. And when we're moving in the plane, it means the same thing. We want velocity to be 0. But what that means is that both components of my velocity vector have to be equal to 0. It's not good enough for just one of them to be 0. They have to both be 0. So I'm going to start with the x component, and let's find the derivative, or the horizontal component of the velocity vector. And that would be 6t squared minus 30t plus 36. So this is our horizontal component, and we want that component to be equal to 0. And since the t is squared, I know I've got a factor to solve this. I'm going to factor out a 6, make those numbers a little smaller. And we get t minus 3, t minus 2. And so t is equal to 2 and 3. But we can't stop there. We need to do the y component as well. Y prime of t is equal to 3t squared minus 6t. And we want that to be equal to 0. Again, I need to factor because we have an exponent, a quadratic. So I'm going to factor out 3t, and I get t minus 2 equals 0. And so t is equal to 0 and 2. And so our answer is going to be that moment when both of these are equal to 0, which obviously is at 2. So for example, at t equals 3, when my x component is 0, that just means at that instant, the particle is still moving, but only in the vertical or y direction. At t equals 0, same kind of idea. The particle is still moving, but only in the x direction. There's no movement in the y direction. But at t equals 2, both of these are equal to 0, and so particle is at rest at t equals 2. All right, we've got one final example here. A particle moves in the xy plane in such a way that its velocity vector is this. So this is the first time we're doing an example where we're starting with the velocity vector. If the position vector at t equals 0 is 7, negative 4, find the position of the particle at t equals 1. This is going to be very similar to how we would work this in linear motion. We're just going to find the position of each component separately. I've got the velocity vector. I need to integrate to find the position. And I have this starting position of 7, negative 4. So the horizontal component of my position vector at time equal to 1 is going to be equal to the position at time equal to 0 plus the integral from 0 to 1 of the horizontal component of the velocity vector, 3t squared minus 4t dt. So this is going to be 7 plus t cubed minus 2t squared from 0 to 1, which would be 7 plus, that's going to be 1 minus 2, and then minus, both of those will be 0. So 7 plus negative 1 equals 6. So this is going to be my horizontal component. And then we're going to do the same thing for the vertical component. Y of 1 is going to be equal to y of 0 plus the integral starting at 0, the position that I know, ending at 1, the position that I want, 8t cubed plus 5 dt. So this is equal to my initial position for y, which is negative 4, plus the integral of 8t cubed, that's going to be 2t to the 4th, plus 5t, from 0 to 1. So negative 4 plus 2 plus 5 minus, and those are both going to be 0 again. And this is equal to negative 4 plus 7, which would be 3. And so my position at t equals 1 is 6, 3.